Welcome guys to this brief introduction to set theory. First of all, let's begin by defining what is a set. Well, a set is just a collection of objects or elements. So you can think about them like plastic bags, like vessels to be filled with objects, with elements. So we denote sets with capital letters, and we describe their elements with braces. What do I mean? For example, the set A is going to be the collection of numbers 1, 2, and 3, and we close our braces. So we are denoting our set with capital letters, and we are using braces to describe their elements. For example, set D is the collection of the shapes circle, triangle, and rectangle. So again, we're using capital letters and braces. So one thing to note with sets is that order and repetition of the elements are not important. Of elements is not important. What do I mean? For example, let's say we have set A, which is the collection of letters A, B, and C, and another set, which is set B, which has the elements A, C, B, A, B. So ABC is the same thing as ACB, since order is not important, and we have two A's and two B's, but again it's not important since repetition in sets is not important. So with these two pieces of information, then we can say that A is the same set as B. Order and repetition not important. Well, a little bit more of a notation. We're going to write this, and it reads X is an element of the set A. So elements of the set are going to be written with lowercase letters, and as always our sets with capital letters. So this little symbol here represents that X is an element of A. So let's say, for example, that we have the set A, and this again is the letters A, B, and C. Then we can say that A is an element of set A, B is an element of set A, and C is an element of set A. Another thing is this notation reads A is a subset of B, of set B. What do I mean with this? Again, so let's say that A is the set 1, 2, 3, and 4, and B is the set 1, 2, 3, 4, 5. Well, then A is a subset of B. What's the meaning of this A being subset? Well, if every element of A is also an element of B, then A is a subset of B. If you think, we can think this with the help of Venn diagrams. Let's say that we have here our universe set, and let's say that we have set B, and let's say that this is set A. In this case, we are representing that A is a subset of B. Now, one thing to note, if A is a subset of B and at the same time B is a subset of A, then A equals B as sets. Okay, another way to write sets, to denote sets, is like this. The set A equals braces, as always. Let's say all the x's that are elements of the natural numbers, and then a vertical line which is going to be interpreted as such as x, let's say, and then we write a condition. Let's say that x is prime and x is greater than 2 and less than or equal than 10. So this is another way in which we can describe set A. A is going to be the collection of all elements of the natural numbers. This vertical line reads such that. So A is going to be all the elements of the natural numbers such that x is prime and is between 2 and 10 without considering 2. So this is the same as writing A equals to, well, 3, 5, and 7 are all the natural numbers which are prime and are between 2 and 10, right? We have, let's say, 3 and 4 and 5, 6, 7, 8, 9, 10. So these are all the numbers that are between 2 and 10, not including 2, but including 10. And from this collection, we need to select those that are prime. So 4 is not prime, 6 is not prime, 8 is not prime, 9 is not prime, and 10 is not prime. So we're only left with 3, 5, and 7. So this is another way in which we can write sets. So let me present to you another very important set, the empty set. Empty set. The empty set is going to be denoted with this sign. This is, as the name says, the set with no elements. Why do we want a set with no elements? Well, if we define the empty set with this as the set with no elements, then we end up with very interesting properties. For example, the empty set is a subset of A, and here in this case it doesn't matter who is A. So this means that the empty set is a subset of every set. How do you prove this? Well, if this was not true, then there must be an element here that is not here. But since this is the this is the set with no elements, then such thing cannot happen. Therefore, the empty set is a subset of every set. It doesn't matter who is A. Okay, let's continue. We're almost over. Let's define the union of sets. We're going to write it as this, and we're going to define as all the x's such that x is in A or x is in B. We can think about this with the help of a Venn diagram again. So let's say that we have set A and set B. Well, the union, which is going to be in yellow, is going to be everything that is colored with yellow. Or maybe you can think about the sets A and B as being like this. Again, let's draw some context. And now we can think of the set A to be here and the set B to be here, and again the union of A and B is everything that is colored with yellow. Another more precise example could be, imagine that A is the set of 1, 2, 3 and B is the set of 3, 4, 5. Then the union, A union B, is going to be 1, 2, 3, 4, 5. So we're going to take all the elements that are either in A or in B. Now let's talk about the intersection of events. We're going to denote the intersection like this, and we're going to define it as all the x's such that x is an element of A and x is also an element of B. We can think about this if we define A as, I don't know, A, B, C, and D, and the set B as C, D, E, and F. So the intersection of A and B is going to be C and D. Why? Because just C and D are the elements that are in both sets, A and B. Or we can think about this with the help of a Venn diagram. And let's say that this is set A, and let's say that this is set B. So the intersection is going to be everything that is colored in yellow. But this is not the only case. We may have something like this. Sorry about the lines, but you get the idea. Let's say that we have set A over here and we have set B over here. Then what's the intersection in this second case? Well, when we have something like this, we say that A and B are disjoint sets. Disjoint sets. Or another name that is used is mutually exclusive. So in this case, the intersection of A and B is just the empty set. The intersection of these two sets in this case is the empty set, the set with no elements. Now let me present to you the complement of a set. So we're going to denote the complement as this C, like it's a power, like if you have a squared, but instead of a 2 you have a C, and it's just all the x's such that x is not an element of A. So let's say that A is the following set, 4, 5, all the way until 10, and let's say that B is the set of numbers 2, 3, 4, 5, 6, and 7. So the complement of B relative to A is going to be the set of all the elements that are not in B but that are in A. So this is the set of elements 1, 8, 9, and 10. So there's a curious thing here. We have to define the complement of a set in relation to another set. So here we're using the set A as the context of B. So let's say, let me try to draw this in a Venn diagram to see if I can explain myself better. So now we have, let's have the set A as all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is number 1, number 2, number 3, number 4, 5, 6, 7, 8, 9, and 10. Okay, and the set B is going to be in green, and B is going to be also, let me just write a small line below the point, 2, 3, 4, 5, 6, and 7. So the complement of B, the complement of all the points that have a line below them, in context or in relation to the set A, which is the set of all the points, is going to be just the set of 1, 8, 9, and 10. 1, 8, 9, and 10. So to define complements, we have to define it in relation to another set. So finally, let me write some properties. The first one is the following: A union B is the same as B union A, and A intersection with B is the same as B intersection with A. This is the commutative property. Another property is the associative property. Union C, and the same thing happens for the intersection. This is the associative. Associative. Now the distributive property. This is a little bit more interesting. The same thing if we switch the sorry, let me write this again. If we switch the union by intersection, distributive, now the complement of the complement is just the original set. Now if A is a subset of B, then we have the following: A intersection with B is going to be A union B is B, A intersection with the empty set is the empty set, and A union empty set is A. The last two, again, if A is a subset of B, then A intersected with A complement is the empty set, A union A complement is B. Here in this complement we are considering the complement in relation to the set B. A intersected with A is just A, and A union A is just A. And finally, what's the complement of the union? Well, it's just A complement intersected with B complement. And what's the complement of the intersection? Well, it's just the union of complements. These two are called the De Morgan laws. So that's it with this introduction of set theory. Thank you guys. See you later.